Hello, everybody. Okay, so thank you for that intro, Phil. I'm going to talk to you indeed about designing for concurrency using message passing. So to start with, I'm going to talk about why are we using message passing rather than anything else for concurrency? I don't know. Then I'm going to talk briefly about message passing frameworks, what they do for you, and how one might use such a thing. And then we're going to look at some design guidelines. If you're designing an application using message passing, what sort of things do you need to think about? And then we're going to do some worked examples. So that's sort of an overview of how we're going this afternoon. So let's start with why do you want to use message passing in your application? And well, the big reason is that you can eliminate all your concurrency bugs if you do it this way. Now, very straightforward, powerful reason. And if you use message passing as the sole means of communicating between your different threads, then all your concurrency bugs go away. Well, at least that's the theory. And in reality, you can eliminate explicit synchronization, which is a large cause of bugs. You can eliminate OS level deadlock. So if you're doing explicit synchronization and you're using explicit mutex locks, then it's very easy to end up with deadlocks. If you use message passing, then that form of deadlock just doesn't exist because the message passing framework takes care of it for you. And similarly, you can eliminate data races. If the only means that you have of communicating between threads is via messages, then you don't have shared mutable state, and consequently, you don't have data races. So these are powerful reasons, and genuine benefits that you can get from using the message passing style. But it doesn't come for free. There is a cost. In exchange for these definite benefits, you have to use the message passing framework for synchronization. If you start doing some synchronization on your side and introducing your own communication paths, well, those communication paths are now not covered by the message passing framework. They don't provide, they provide their own set of guarantees and their own potential sources of bugs. That is, so anything you do that's out of the scope of the message passing system has whatever issues or benefits it has on its own. It is not part of the message passing, and so it's not covered by the message passing benefits. So if you say we get all these benefits for our entire code base, you have to use the framework for everything. And consequently, as I say, you have to avoid the shared mutable state because shared mutable state requires X-zone synchronization. We're trying hard to avoid synchronization and put it all on the framework, so we have to avoid shared mutable state. I mean, it's always a good plan in multi-threaded systems to avoid shared mutable state when you can. So that's just a standing guideline, but using message passing can make it very explicit. We don't have state that is shared. What we do is we pass messages. And then the big one is, I say the big one, it's as if the first two are not big enough constraints on you already. Third one is you really do have to change your design approach. If you're used to thinking we have shared state that that is either has internal locking, if it's a data structure that's designed for concurrent usage, then it will have some form of internal synchronization. So you might have a shared queue or a a shared hash map that is designed for concurrent access. And so then each thread, they have this shared data structure that all the threads can access and use together. If you are moving to message passing, then you need to give up on that. You do not have this shared data structure of any description. There's no such thing as a shared data structure that's designed for concurrency that you are also using alongside the message passing, because that then is outside. That is communication that's outside the framework. So that is not something that we covered. So you need to rethink your approach. If you want to share state, then you send a message. And that has to be the one and only way that you do it, which, it requires rethinking, and because it explicitly introduces the asynchronous nature of this into your code. If you have data structures designed for concurrent access, then often it will look like a simple function call, and then it's going to lock the mutex, which might introduce a wait. It's going to do the data access, it's going to unlock the mutex, or equivalent synchronization, but it's still straight through code. If you're sharing state with messages, then you have an explicit, I am sending a message. And then at some explicit other later point, you receive a response message. And so you don't have that single straight line code unless unless your message passing framework somehow works, like with C++20 coroutines, and so then it can you can co-await for an incoming message or something like that. But still, you need to make sure that it works, and it's then very explicit that you've got this synchronization that you've got to do. So you do have to change your design approach and think very explicitly in terms of messages. Okay. So the hook was, well, if you do this, then all your concurrency problems go away. Well, not entirely true. No, there is still a potential for race conditions. And the most obvious of which is which message gets there first. I have two components that are both sending a message to a third component. If there is now a race condition in the sense that which message gets there first is now up to the framework, and it might be up to random timing of the OS scheduler and the CPU as to which one actually wins internally in the framework. And so there is still the potential for race conditions. And hopefully, though, they are benign in the sense that they don't end up causing bugs. But there is still the potential for behavior that is different depending on the order of messages, the order in which things are processed, and how things arrive from different parts of the concurrent system. If you have a system which is very explicitly distributed, so that the messages are actually passed over a network, then this becomes very, very apparent because network timings can vary quite considerably. And so the race conditions show up much more readily. But the race conditions still there, even if it's all running on a single CPU. And then there's still the potential for message deadlock. Now, this is not OS level deadlock. You're not you're not having mutex blocks that are blocked, but you can have two elements that are waiting for messages. And so node A sends a message to node B and is waiting for a response. At the same time, node B sends a message to node A and is waiting for a response. Both of them waiting for a response. Both of them not going to do anything until they get that response. You can have deadlock. So you need to think about this when you're designing your system. Now, this is a application design issue rather than an OS level issue. It's or a library implementation issue. It's about making sure that you don't ever get into that state where there's things which are potentially waiting for messages from each other, and that they are not. Make sure that if your node can potentially be waiting for a message from somewhere else, then if it receives a message that is different to that, then it can still respond to it correctly. Usually frameworks will allow you, provide a way to say, I can wait for 5, 10, 20 different types of messages and add associated handlers, so that you then don't need to explicitly say, well, I'm waiting for this message. So what happens if another one comes in? It's like, well, no, I've defined a handler for when I get that message from node B, and it doesn't matter whether it's the thing that I was originally waiting for, or it's a different message. When it comes in, then I know how to process it. So like I say, that's an application design issue, but it's still something you need to pay attention to. And then we have a new problem, which is the potential for dropped messages. I know, as I say, a new problem is it tends to be more specifically a problem with network stuff. And if you're communicating over a network, there's always the potential for network dropouts, packets not getting there, whatever. But even within a process, your message framework might have some form of bounded queue, or even if it's technically unbounded, then it can fill up. You can run out of usable memory, and so the messages might not get to their intended recipient, and you need therefore to think about that and how your application is actually going to process that. Is it resilient in the face of dropped messages? Or if a message never gets there, does that mean that another component is now just going to not be able to do any more processing because it's waiting for this response that's never coming? And so overall, it's still not the silver bullet that the top level hook promises us. It is still something that we need to pay attention when we're designing our applications. You can't just say, well, we'll use message passing, all our problems are solved. Well, you still need to use it correctly. And so then that is the big issue, is how you do that. Okay, so message passing frameworks, what is it? Well, fundamentally, a message passing framework is something that manages the delivery of messages between independent elements. It's in charge of how the messages get sent, how they get delivered, making sure they end up at the appropriate target, dealing with any potential races in terms of actually making a decision about which message comes first, and then just generally dealing with the messages so that you don't have to think about how you deliver them. All you need to think about is, where is it going? And the reason that you use a framework is so that you can focus on what you're trying to achieve. You want to focus on the content of the messages. What data is it that I want to get from A to B? It's not just that I want to send a message. I actually there is a purpose to this message. It's going to be transferring some data. What is that data? What is it we're trying to pass? And then you need to think, well, where's it going? You want to think carefully about which of the elements of your application are going to receive the messages. When I send this message, is it going specifically to that bit of code over there? Or is it going to be broadcast to a whole set of receivers, and each of them is going to get a copy? Or the first of many is going to get a copy, whichever one picks it up from the queue first? Lots of things, but you need to want to think about this at the application level and not have to worry about how to code it up. So your framework deals with dealing with the delivery. You just specify, where is it going? What is my message? Where is it going? And then, of course, you also want to think about what you do with the message when you receive it. So these are the big things that you want to think about as a developer. Fundamentally, you want the framework to take care of everything else. Next, the framework takes care of the delivery mechanism. You say, I've got this message, it's going to node A and node B. And then in nodes A and B, you say, when I receive this message, this is how I want to process it. You don't want to have to think about how the message gets there. You just want to code up where it's going, code up what it is, code up how to handle it. No, don't care where it came from, don't care how it got here, want to know, how do I handle this message? Framework takes care of the delivery mechanism. So one way to do that is that, and fundamentally, is to think about your application, as I said, or microservices. You can, I refer to them as elements and nodes. Sometimes people call them actors, but a microservice is what it is. It's a tiny little piece of code that's running that has a set of things that it does, each of which is done in response to receiving a message, and it sends some messages to other components to get them to do their bits. It's a microservice. And the API that's exposed for your microservice is the set of messages that you can send to it, and then the message that it then sends on to the other parts of the system. And then, so now we talked about the message passing framework makes sure that messages get where they're going. And one key aspect of that is usually that they can provide a way that you can say, this microservice can only handle one message at a time. That can be important if your handlers are essentially defined as some sort of callback. So you say, well, if I receive this message, call this function. If I receive this other message, call this different function. If I receive a third type of message, call this third function. And it's like, well, together those three things provide a microservice, and I only want it to be processing one message at a time. And usually your message framework will provide you a guarantee that you can do that, because otherwise what you end up is you've now just got your three tightly related functions. They might be running concurrently, and then they need internal synchronization. And if they need internal synchronization, then we're going to have to use synchronization that's not part of the message framework. And therefore, we've lost what we start. One of the benefits that we were looking for is to say, well, all the synchronization is via the framework. So one way that it does that is by providing this guarantee that each microservice only processes one message at a time. And so therefore, it doesn't need any internal synchronization, because the three functions for handling the three different types of messages are never running concurrently. They can therefore all access the same bit of data that belongs to this microservice. Sometimes you can also add a guarantee that all the messages for your microservice are on the same thread. That's not necessarily something that you desire. It's not necessarily something that the framework will provide, but it can be a useful thing, because that can mean that then you can use thread local variables and things to store data. Not usually something that it's particularly important, but sometimes it matters. If you're calling into third-party libraries, often GUI frameworks require that all the code that interacts with a particular GUI element all happens on the same thread. That might be a top-level window that's that GUI element, or it might be a smaller portion of the GUI. But there is usually that requirement, or there can be that requirement that all the calls relating to a particular thing are done on the same thread. So if your message passing framework provides that guarantee, then that makes it easy to do. You just say, well, I have this one microservice that relates to this given GUI element, and then I know that every message that gets processed by that microservice is on the same thread and can therefore interact nicely with the GUI element without also then having to proxy to a particular thread for doing that. I know some database systems have the same thing too. a given database connection is tied to a thread. You might be able to have multiple database connections within the same application to the same database, but each connection handle belongs to a thread. I've certainly seen that before. So this same thread guarantee can be important. So your framework might well provide that too. But again, it depends on what the system that you're running on. If you're trying to take advantage of the hardware parallelism that you've got, then you might find that running on the same thread requires that your microservice is then restricted in the scope of which parts of the system it can use if you've got a non-uniform system. And so that might not be viable. But obviously, you know what your system looks like, and the framework presumably is designed to deal with that. And then there's a final thing. The framework might, rather than having a dedicated thread for each microservice, it might have a thread pool, in which case then it might give you control over which subsets of microservices share a thread, because it's like, well, if they do share a thread, then you can't have a function from service A running at the same time as a function from service B, and that may or may not be important. So that might be something that you need to look at. There is whether they can run on the same thread, or whether they are required to potentially run concurrently, in which case then they need to run potentially on separate threads. Again, and if you don't require that all handlers from the same service are run on the same thread, then that works nicely with the thread pool, because then it's like, well, a handler for node A can run on the first thread, and meanwhile the handler for node B can run on the second thread. If the first handler for node A finishes, then now node C can have a handler on that first thread, and then the next handler for node A might end up running on the second thread in the pool. But that's okay, because we've decided that they don't need to run on the same thread, and they can all run on the pool. Whereas if they need their own dedicated thread, then you end up needing to worry about that. So you might expect that your message passing framework will allow you to have some sort of control over how these are distributed between threads. But again, that depends deeply on the framework. And mostly I'm talking here in general terms rather than about anything specific. So that's how we're scheduling the handlers. But what about actually delivery? Well, your message framework may have just a fixed form of delivery. It might say, well, everything is just function calls within process. Everything is messages sent by UDP or whatever. Or it might give you a choice. You might be able to choose between various in-process, cross-process, network mechanisms. Or it might just always pick one or the other for you. But one of the key benefits of using the framework is then the code itself doesn't care. I write a handler for message of type ABC. I don't care how it got to me. If I'm sending a message of type ABC, over to node X, I don't need to care how it gets there. I just tell the framework, this is the message, this is where it's going, you take care of the delivery. And so at some point, yes, you're going to have some configuration, whether it's configuration in code or configuration in a config file that tells the framework what delivery mechanism to use. But that can then be quite isolated and high level and separated from the code that's actually sending or receiving the messages. So, that's all very theoretical. But the point is that we need to use real message passing frameworks. And unfortunately, they often mean that there's some boilerplate. You often find you have to write code to drive a message loop yourself if by using the widely available ones. And that's a bit of a pain. So I strongly recommend that you have some team in your company whose job it is to deal with this boilerplate, wrap it up, have a code generation tool, put a library around it, so that then you've eliminated the boilerplate and it's all much more straightforward for application developers to use. Okay. So next up is actual design guidelines, how we're going to look at what you really need to pay attention to when you're designing your system for message passing. So probably the most important aspect is that each microservice should be focused on one task. So this is the single responsibility principle in action. What is it that this microservice is responsible for? You don't want to make that too large. You don't want to say, this microservice is responsible for managing the whole GUI. You don't want to say, this microservice is responsible for accessing the file system, just as all the files. You want to make it focused, so that it is simple, clear, has very explicit responsibilities, and make it easy for you as a developer to understand what it's doing, for your fellow developers to understand what it's doing, make the system easier to think about, easier to debug, easier to test. If you think microservice rather than monolith, we're trying to avoid having the entire application as one microservice, because then it's not a microservice. That's just a great big blob. So they need to make each one focused. What is the task of this microservice? And then related to that, they need to be independent. So that you don't push it so far that you say, well, this microservice is responsible for initializing my window, and this microservice is responsible for putting some text in the window, and this microservice is responsible for dealing mouse messages in the window, because they all need to interact with the same window. So there needs to be some sort of communication between them to deal with that. And that means more messages, and they can make things more complicated. So if you cut, it's sort of the counterpoint to the focus. If you cut things too fine, then your tasks are no longer independent, and so you need to have them as small as possible, but no small. And then we need to make sure that the messages are value types. And this is essentially another way of saying there's no shared state. The point is that you can copy a message and it doesn't matter. The framework can copy it as many times as it likes, or even if that's, when I say copy, there might be technically a C++ move to move the data between objects. But the point is that you give it a value, it trundles around. It doesn't matter which object it is that owns that value. So std string, perfect example. It has a value. It is the content, the sequence of characters that's in it. It doesn't matter whether the actual address of those characters is the same when you transfer it to another object or not. Has it got the same sequence of characters? And so you can't tell. It doesn't matter whether it uses a small string optimization. It doesn't matter whether it gets serialized to a file and read back again, or sent over the network and reconstituted. The point is that it's the value that matters, not the identity of the object. And yeah, that makes it easier. It means you don't have the synchronization, you don't have that shared state. It means that then the framework can serialize and deserialize it across a network without you having to worry about what that means and whether it's the same object or not, because it's got the same value, so it's all good. And you need to avoid blocking. I mean, this is pretty much always a good idea in multi-threaded code, but in lots of places, then you end up with blocking because you're blocking waiting for a mutex as synchronization. This is an essential part of normal multi-threaded code that's not using microservices. But if you're using microservices, you want to avoid that. You want to just dial it back so you don't make blocking calls. If it's a call that should be blocking, then move it to a microservice. You send it a message, and then you get a response when it's done. Obviously, you have to take that. There has to be some granularity at some point. If the only way of achieving something is an OS level blocking call, then you need to make that blocking call. But you want to isolate it in its own little microservice, so that it is then processing one message at a time. And it does this. It receives a message. It does the blocking call. It then returns the response, and the things that interact with it then don't need to worry about that it's a blocking call. They just send it a message saying, can you do this? And then it sends a message saying, oh, I've done that. And they don't need to worry that at the OS level, it's a blocking call. And then one thing to think about is that if the entire API of your microservice is the messages that come in and the messages that go out, then this is a state machine. And so there is a heck of a lot of literature on how to design state machines. And so we can utilize that. We can design each microservice as a state machine and use whatever state machine framework you are most comfortable with, or your company uses already, or whatever like that, just to build a state machine. And then that makes your microservice implementation just that little bit more regular, more straightforward. Okay. So that's abstract stuff. All the theoretical sort of design guidelines. Let's actually have a look at some worked examples. So the first example is going to be the classic dining philosopher's problem, commonly used for multi-threading things, talk about deadlock and synchronization, things like that. So the problem for those people not familiar with it is we have n philosophers sat around a table showing a large plate of rice. And they're going to sit, they're going to think, they're going to eat. And for some bizarre reason, they don't have enough chopsticks to go around. They've only got one chopstick each. It's really hard to eat rice with only one chopstick. So they're going to need to share. They start by thinking, and at some point, somebody is had enough thinking. They want to eat some rice. They try and pick up some chopsticks. They can't eat if they haven't got both the chopsticks. So if they can only get one, they need to wait until they can get both before they can start eating. And if they've got both the chopsticks, then they will eat for a bit and they'll put them down again and then carry on thinking. So the crux of the design of this as a multi-threading issue is, how do we deal with making sure that the philosophers get to eat, and they don't get the case where every philosopher has picked up one chopstick and nobody gets to eat. So that's the crux of the problem that we're trying to solve. So one potential way to do this is that we have multiple actors, multiple microservices, one for each philosopher. We have a separate one for I/O, because I/O is commonly blocking, and we don't want to interrupt our philosophers and their thinking or eating just to print messages. we're going to have another microservice that's responsible for managing timing, so that if a philosopher wants to wait, then they can send a message to the timing microservice saying that give me a nudge in 5 minutes because I'm going to want to eat then, or whatever. And then we're going to have another actor or microservice that's responsible for managing the chopsticks. So the IO actor is really just straightforward. It has the message type that it's going to have, and in this case, some form of string. And the message handler is just going to say, output the message to standard cout. Dead easy. Then it. The timing actor, a little bit more involved. There's more to it, because it's going to want to receive a time to say, well, I'm after. Actors are going to say, notify me in 5 minutes, or rather, yes, they will work out 5 minutes time is this particular point in time, so notify me then, because obviously you need to deal with the fact that there's message delays in sending. So you don't want to have the actor says notify me in 5 minutes. The message framework takes a certain period of time to get that message to the timer, and so now actually, by the time the response comes back, then it's been 6 minutes, 7 minutes, or whatever, because of timing delays. So you need to be prepared to think about that. So we send an absolute time when we're trying to, and it should of course be steady clock time point that specifies the time, and then we also specify the target that it's going to, and then when that time comes round, then the timing actor sends a timer expired message to the target at that time. The philosophers are a little bit more involved, but they're really quite straightforward. They have 3 states. They are thinking, they are waiting for chopsticks, or they're eating. And in each state, we can process a particular set of messages. We think state machines. So we have incoming messages. If you're thinking, then the incoming message that we're waiting for is a timer expired. But when we start thinking, then we'll set the timer. We'll output some text to say we're thinking. In waiting, then again, we're waiting for the got chopsticks message, and we'll output some text and we'll request some chopsticks. And again, eating, we'll output some text. We'll set a timer this time. Again, how long we're eating, then the timer expired message just sets us back to thinking. And so we just have these 3 states. A nice little state machine. So we go around the loop. So how do we code that up? Well, when we start thinking, then we get a random duration. We send a message to say we're thinking. And we then actually send a message saying, can I have a timeout that from now plus our thinking time, and send it back to me? Okay, that's straightforward. And then when we get the timer expired message, well, we only have one sort of timer expired message, so we need to check, are we thinking? If we're thinking, then we need to respond to that by saying we're finished thinking, and we change to waiting for chopsticks. And if we're waiting for chopsticks, then we print some text, and then we send a request for some chopsticks to the server. So, which chopsticks are we waiting for? We're looking for specifically this chopstick and that chopstick, not just any old 2. And that would be an alternate design, is to say, can I have 2 chopsticks, please? And leave it up to the server to choose them. But the classic design is to say, well, each philosopher has 1 chopstick to their left and 1 chopstick to their right. And he or she only cares about those ones. It doesn't matter the ones over the other side of the table are free or not, because they can't reach. So then we're updating these. Now, all these message handlers are really quite small and simple. We're going to when we get some chopsticks, we just start eating. Change the state to starting eating. That's straightforward. Eating looks very much like thinking. We have a duration of time. We send a message. We ask for a timeout. It does then mean that now we need to update the timer expired handler to say, well, okay, well, what if we were eating when the timer expired? Okay, in this case, then we finished eating rather than finished thinking, and we need to hand in the chopsticks that we were using, and then we can change the thinking. So this is now sort of the most complex of the message handlers, because it's actually needing to deal with multiple possible states that we could be in when we get it. So you might want to factor that out into separate state-specific handlers. Okay, on the server side, then server is managing the chopsticks, so we have to request some chopsticks. If somebody has requested some chopsticks, we say, well, if they can have them already, then mark them as used and send them out. Otherwise, then add a list of philosophers waiting for chopsticks. When the chopsticks come back, mark them as available, and go through the list, checking to see who's waiting for chopsticks. Are the chopsticks they're waiting for available? If they are, use them. Then notify them they can have their chopsticks, otherwise, and remove them from the waiting list. So we can go through the whole waiting list when we get back the chopsticks, see which process, notify all the waiting philosophers, which, well, it's only going to be two of the waiting ones, but so you could optimize this to say, well, who could be waiting for each chopstick? But the simplest way to code it up is nice and clear, and then anything else is an optimization. So notifying chopsticks is just notifying philosophers that they've got the chopsticks is just send them a message. But we do need to keep track of whether or not the chopsticks are free. So we have our map for that. Now it's all very, very simple code. And at each point, then we can look at the server in isolation. We're getting messages. Where are we getting from? What's the internal state? We're looking at the philosopher. What's the internal state there? You can focus entirely on that. It doesn't matter what the state of the other philosophers could be. It doesn't matter what the state of the other system could be. You just need to focus on what's the state of this particular object. It's all very straightforward. Okay, so the second example is a robot control system. So we have a robot with many moving parts, robot arms that got to move around. They've got lots of joints and motors that control all the bits. So it might have a grabby hand that opens and closes. It then has various angles that it can move, and then the whole arm can swivel and various things like this. So each part has its own actuator. They're all coordinating. We want the control code for this to run on a single thing, but multi-threaded, so that each actuator has its own little handler and a microservice, and then concurrently with the coordination code and concurrently with any control code for the other actuators. So it's not that, well, I'm trying to move this motor and I need to wait until the motor over here is finished doing its processing before I can actually start messages sending that one to. So you need them to run concurrently where you can. But obviously the synchronization of that then becomes tricky. So use our message passing framework. So you have multiple actors. You have one for the central coordinator that's determining which motor needs to move where. We have one for each actuator, and then we have something for controlling the timing. So if we're going to move a robot, our robot arm to some sort of large scale position, as in the robot arm needs to be over here on the left, picking up an object, and therefore it needs to have its grip closed to grab the object, and it needs to be positioned over the object. Alternatively, it might be that it needs to be all the way over here on the right and deposited the object with the grip open. So we've got big level movements that it needs to do, but that then requires lots of individual positions for all the individual different actuators that control the different parts of the motor of the robot. So the coordinator has a large scale position that we're setting. And so we have a message to say, set this large scale position, but then it needs to send messages to all the individual parts. Say, I want you to move to this particular position at this target time. So that we can, so that it doesn't matter quite at this point. We're trying to move from here to over here, and it doesn't matter whether I move the wrist first, or close the grip first, or move the one part of the arm articulation and then another part of the arm articulation. As long as everything can move in a smooth, continuous action, so that everything gets there at the same time. See, sometimes there's things in the way, so you have to design the overall path, and you split up the movement into, well, first I need to move to position 1, then to position 2, and things. But still, each part you move, all the different parts of the robot need to move so that we end up overall at the right position at the given time. So then we have the actuators for each individual piece of hardware. And again, now we're looking at something that's far more hardware specific in terms of what the actual code does. So here we're looking at saying that, postulating that the hardware has a specific API. We might move at a given speed. So and then it just keeps moving. The motor keeps turning until you say stop. So the first thing we're trying to change what it's doing. Say stop moving. Now then we can say, well, where are you now? What position? How far on the range of movement of that particular motor are we at? And then we can look at where we are, see where we're trying to be, and then look at how long we've got to get there, and then say, well, okay, if we're not where we need to be, then we need to get moving, and we move at the speed that takes us there so that we arrive at just the right time. So if I need to move from over on the right to over on the left in 3 seconds, then I'll move so that in exactly 3 seconds I'll get there. If I need to move in only 2 seconds, then I need to move a bit faster. And at some point, then that's be too fast, and the hardware can't do that. But until we hit that limit, then we can try and scale things sensibly so that the robot moves smoothly rather than jerking around. Then if you move at the fastest possible speed for each individual thing, and then sit there with waiting, then it tends to end up with jerky movements that if you're moving liquids, then it can slop and things like that because you've moved and sudden stop. Whereas if you move slowly, then things move nicely. So having that, well, how long have we got? Let's move as slow as we can to make sure we get there. And it is a reasonable sort of way of doing things. And then we send a timing request saying, well, at the appropriate time, then notify me that we're there, because the time has elapsed, because we're going to need to tell the hardware to stop moving, because we've just said it starts moving until you tell it to stop. So we need to schedule a time to say, oh, we're done now, stop. So then, when we get our timer expired message, then we stop moving, and we can send a message to the controller saying we've reached the position that was requested. And so it's a very straightforward message response. The central coordinator is then a bit more complicated, particularly if you think of adding sequence and movements. If we've got, like I say, if you've got to move an arm around an obstacle, then you need to, as a system designer, you're looking at the large-scale movements of the robot arm. You can plot out the various positions it's got to be in, and then so you say, well, I need to be in a position and they need to be waiting to get to position 1. Then I need to wait to get to position 2. Then I need to wait to get to position 3. So that means you need to add more states to your state machine for the central coordinator. And then you need to add messages for setting those positions and notifying when you get there. So we have our bigger state machine. And we have a message at the top triggering sequence 1. When in idle state, we trigger sequence 1. So then we start waiting for position 1. So we need to send a message saying set to position 1, send the actuators their requirements. When we get the response messages back from each of the individual actuators, then we know that we've reached position 1. So we can move to position 2, which then does the same sort of thing, send the messages, wait for the messages. Eventually, we've reached position 2. We can start waiting for position 3. We send the messages, we wait for the messages, and eventually we're done. And so we send a message back, and we move back to idle because we've reached position 3. And so we have a large-scale sort of state machine that designed around all these things. And the response messages that we get for each, I know it's going to be the same. Actuator 1 reach position, actuator 2 reach position, actuator 3 reach position in each of the 3 states. But obviously the handling is going to be different because where you go next is different. Classic state machine stuff. So when we get the message for triggering sequence 1, then all we start with is saying, okay, well, when do we need to be there? And set the state to say we're waiting to get there. And send ourselves a message to actually trigger that. It's very, very simple, and then everything, it just triggers that state transition, and so now we can then wait for the next set of messages, and we'll see what comes in. So then when the actuator 1 reaches position, then now we can, well, which state are we in? Well, if we're waiting for position 1, then we can say, if we're at position 1, then position 1's been reached. And if we're not, then we're probably waiting for something else. And so that's okay, we can break. And then, of course, there'll be other code for all the other states if we're waiting for position 2, waiting for position 3, etc. When all the actuators have reached the desired target, we get a position 1 reached message. Then we can send ourselves a request to move to position 2, which just then repeats the sort of process in terms of sending the actuators to the desired positions. It does mean that if you end up with multiple movements, complex movements, multiple sequences, this becomes a big state map. So you might then want to look at sort of expanding that, doing table-driven stuff, state machine things, possibly state machine config files, particularly if things are dynamic. You want to be able to have user-defined sequences that are loaded at runtime, that sort of thing. So you can do that. There's lots of different ways to do it, but fundamentally, this is just state machine processing. There's a whole lot of ways of doing this. Lots of state machine frameworks have things for dynamic state maps or state map or table-driven state maps and things like that. So it's all something that there's plenty of literature on how to do this. It's just a state machine. It might be a big complex state machine, but it's just a state machine. So this is again something that we can readily do without having. And again, you don't have to worry about any concurrency in this. This is just the messages coming in. Is the actuators have arrived at the right positions? Which positions we need to do next? Oh, the timer has expired, so need to deal with that. These are all straightforward messages coming in. Don't need to worry about concurrency. Just focus on the states. So, to summarize what we've been covered, a framework allows you to focus on the messages and their content, their targets, rather than the delivery. And it allows us to eliminate explicit synchronization, but we need to focus our microservices on just one task and make sure they have minimal overlap in the responsibilities with the other microservices to avoid excessive communication between them. Messages should be value types so that they can be freely copied and moved and serialized and deserialized by the framework without the message handlers needing to worry about that. And if you've got blocking calls, move them to separate microservices. And then finally, if your microservices get complex, you can model them as single-threaded state machines. And that is a big bonus from doing it this way. Okay, in case anybody didn't know, I read a book on concurrency. There's a little bit on message passing frameworks and state machines in there. So you might want to take a look. Okay, so that is it from me. If anybody has any questions, then I'm happy to answer them. I see that there's something on the Q&A tab. Can I suggest some message passing frameworks for C++? So I'm going to tell you about some ones that I'm aware of. I'm going to say none of the readily available libraries that you can get are really nice. In all the companies that I've worked at where we've wanted to do this, we've ended up having to wrap them in our own custom framework to make it work. But things that you can use, I've put on a slide for that. So, here then. So for communication, then 0MQ does the message processing, but there's quite a lot of overhead on that in terms of boilerplate. Then there's something called the C++ Actor Framework, or CAF, I think it calls itself, which provides a means of defining actors and communications. In my book, there's an actor framework, a very basic one described. There's some source code for that. And of course, you can write your own. So there's various options. None of the ones I've seen are ideal. There's definitely something that's, if somebody's got some spare time or looking to create a product, then there's something there that something that people will find useful for. Because, like I say, multiple places I've worked, we've ended up doing our own, which have been a wraparound of one of these, and it adds overhead. You'd rather it'd be nice if you could just take something off the shelf that covered all the bases, but no, the readily available ones do not. Okay, so then we have another question. Why does a coordinator need to send a separate message to itself for arrived at position 1 when it detects that that's happened? Can't it just immediately start the work to move to position 2? And so, yes, conceptually you could. You could put the work in line in that, but from a state machine management perspective, it is easier to, rather than putting the work back in there, then you can specify that is a separate transition to a separate state, and it makes the message handler smaller, and allows the framework to intercept it, and allows you to put some logic on that. If you've got using a state machine framework, then you can say, well, I'm sending a message. So when I start doing the move to position 2 stuff, then I do all my starting to move to position bit. I've got a entering state type hook type thing. So you might want to do that, and then have common code between the two bits. And so rather than having it all being in one thing, then you can then have it as have a separate message and a separate handler, because it's very much about what you're doing, how you're designing your code, and making that easy for you, rather than trying to just have everything in one big function.
Okay, thank you.